Okay, so here we go. Don't have to see that. All right. Now this one's weird. So again, when you're reading a question, in how many ways can four tires be arranged on a car? Are all four of those tires different? And that's the question. And it actually is implying that they are. As a matter of fact, how many people are driving? Sorry, we're going to make the other people jealous. My daughter just started. You guys are going to be really jealous. They have a freshman sophomore building, and no one uses the lot. So she's already driven to school a couple times. Oh, isn't that cool? But then she's going to lose it next year because she's a junior, unless she wins the lottery, like they have a junior lottery here. But the car tires often get rotated because then they start getting worn differently because cars aren't perfect, and it also depends what happens out in the road and so on and so forth. So what I'm just getting at is there are differences. So I have one position. Let's say that's the front driver side. How many tires can I put in that position? How many different tires can I choose to put there? Four. I put that tire there. So now let's go to the other front. How many do I have to put there? Three, and then two, and then one. Fundamental counting principle, which is 4 factorial. I'm going to give you a heads up here, by the way. This is a permutation because we are actually saying the order matters where I put the tires because the tires are different, quote, quote, quote. So actually, 4 factorial can be a 4p4. Those are all equal. So again, it is kind of weird that is these are all intertwined and related. I guess is the best way to say it. I know Mr. Stronowski has a worksheet where he asked them, and it was asked of you in there too. I don't know if you wrote it, like what should I do, and then actually do it. And then this could either be the fundamental counting principle or a permutation. It's both the same thing. How about the second one? What is that? Combination. I mean, there's no other way to say it. It's not, the order doesn't matter. All that you're doing is how many different teams of 11 soccer players can be chosen from a total of 16. It's just you're on the team. There's nothing about order or anything like that. Now, if it was a permutation, if order it did matter, it could be a fill in the blanker because that would be a 16p11, which is 16 times 15 times 14 times 13. You get it? You understand what I'm saying? But you stop at 11 blanks, not 16 blanks. All right. And then that's why you don't stop at one. 16p11 would be 16 times all the way down to five, maybe. I'm trying to think of, how many blanks there would be. Not one. Okay. Anyway, it's all good. All right, and then I'm going to be lazy and give you some writing from this side. I don't feel like writing again because it is kind of hard to write on the screen. Okay, we haven't done this then. Oh, that's what I wanted to do. Let's go to this real quick. I hope I still have this written. I did want to go to worksheet 2, which was this one. I thought I wrote on it. Let's see if I did, and it's still here. Nope. Shoot. Wasn't worksheet 1. Where's my lottery thing? I lost my lottery. Was it on this one, number 27? Oh, okay, this is where I wrote it. Good, there's my work. Okay, so I wanted you to understand this. First of all, here's that answer. I know I have that on the pile here. Does anyone remember getting 584 million? Blah. Okay, good. And then look at Powerball. That's the difference between the example that I had for an old Mega Million. So I'm sure that's way off too. I think I said 52 C5 or maybe 54 C5, and then 26 C1. And then those numbers were a little bit smaller. So I had somebody last hour divide by $2 just to see how many possible tickets there are. There are 292 million different Mega Million combination of numbers. That's how many unique tickets there are. So if you bought one ticket, this is the probability that you would win. And that's what I want to introduce today. We haven't talked about probability yet. We've talked about how many ways things can occur. Now, what's the probability of that? How many tickets you bought compared to how many tickets there are. That's why we shouldn't be playing the lottery, but we play it for fun. And it only costs a couple dollars. But then look at this. Sometimes Powerball is over $1 billion. It's very rare. So some people might say, well, then I could buy every single ticket and guarantee I win $1 billion. What are the problems with that we talked about? Another winner? You have to share? Government. Boy, what a problem government is. Oh, he just said that on YouTube. Let's go get them. They're going to swarm my house. No, the government takes an extraordinary amount. As a matter of fact, not government related, but if you win $1 billion and you decide to take the lump sum, you don't get $1 billion. That's another thing. You get the $1 billion if you decide to take it in payments over 20 years. Now you spend all that money on those tickets, you're not going to recover that money for many years. And also the other thing, if you do take the lump sum. So they don't tell you those things until, well, you can look it up, but some people don't find that out until they actually win. So all right, so what's probability of an event? Probability of A, favorable outcomes for the case of the tickets for the lottery. The ticket you bought, that winning is a favorable outcome, but you only have one chance if you only buy one ticket, divided by the total number of possibilities. Okay? And then two key features. We talked about this with statistics. The standard normal curve, the area under that curve represents possibilities in percentages or decimals. The area all adds up to 1 or 100%. So probability is always written as a decimal, fraction, or percent. You would make your choice. Must be between 0 and 1. It could be 0 or 1. The word between means not including. I should say including. We could say, what's the probability? I don't know. I can't think of something where the probability be 0, but sometimes the probability is nothing. And then sometimes the probability of one event is 100%. So probably an incorrect word between. Technically, that means not including. Blah, 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 blah. Okay, good. All right, and then I'm going to be lazy on the last two because they're super simple. Flipping a coin. What are my possibilities? Heads or tails, right? So that's the sample space. Ain't no thing. Chicken wings. Then I'll go into the writing of blanks on the next one. Okay, so let H represent the event of flipping a coin and getting heads. T, tails. What are each probability? And I think we need to add to this, all right? But here's how it's written a lot of times. Probability of H means probability of heads. Obviously, there's two possibilities. Heads is one of them. So obviously, we know 50% chance of flipping heads, 50 for tails. I do want to put a word on this that I did use later with period 2. What we should be saying is if a coin is flipped again, does the probability of it landing heads change? Do you think it is or isn't? Does the first spin, roll, flip, sorry, couldn't think of the right word, affect the second flip? Yes or no? As a matter of fact, we're going to talk about roulette again. Somebody asked me if I played roulette ever before, and I said, no comment, none of your business. No, I'm just kidding. But also on the roulette wheel, like I know I'm talking about a lot of gambling. They and notice in that movie too, why does the casino win? What ensures that the casino wins? Does anyone remember this from the movie? Roulette wheels, you got numbers, you got black, you got red. You had your hand up first. There are that is zeros too. That's right. But also, what color are they? They're green. So you can bet on red and you can bet on black. And you would think that is a 50-50. Actually, it goes red, black, red, black, red, black all the way around the wheel. The casino wins because of the greens. That's why they win. All right. Eventually, over time, a green will come up. Now, people can bet green, but the odds that they give out are not equal to how many greens are on the wheel. It's less than that, the payout. So that's why they also win that. But they do pay out 50% on red or 50% on green when there's less than a 50% chance of getting red or green. That's how they win. But also, what's funny is they have a sign, an electric sign, and they have the last 10 rolls or spins, not only number but color. And it's always hilarious when the last like 8 colors that came up are black, 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 black. So what does that make people think they should run and do? Run and bet on what? Red, well, or actually, it's the opposite. People think, well, it's got to be red at some point. All these, so I'm going to bet red, and I bet you it's going to happen. Well, eventually it will, but it has nothing to do with the 8 previous rolls being black. So I guess one way or other, you think something, and that's why they do it. They get people to rush tables so that, oh, I got to go bet on that. It's going to happen. So the word I should put up here is these are completely and totally independent events. There's a big deal about probability of events being dependent or independent of each other. Rolling the first coin is completely independent of rolling the second coin. I actually should reverse that. Whatever I get in the first coin has no bearing on what I get on the second flip. All right, none whatsoever. Okay, now I'll stop being lazy and go to this page. And then we'll go ahead and fill this out pretty easily. All right, so sometimes it's good to do a probability model and then to see all the things and attributes that we talked about here. So, we always get these fun probability questions. Hey, we got all this fruit. Now reach in and grab a piece of fruit. What's the probability that you get? As if we care, right? 5, 4, 9, 12. There are 20 pieces of fruit. So the outcomes for oranges. I'm just going to put an OR. We'll be real lazy here today. You got a 5 out of 20 chance of getting an orange. And I swear to dog, if you do not reduce your fractions, I will take a half point. It's a fumble. Just scared her. Yes, you must reduce your fractions. All right. And then I guess I could put below here that this is 0.25. So and then that would be 25%. Okay. And you get it. You get it. This is all Mickey Mouse stuff. All right. So then for apples, let's just put AP. That's 4 out of 20, which is 1/5, which is 0.2. And then I just want to get my decimals here. Don't want to make up stuff here. Apples, kiwis. I do like kiwis. 3 out of 20. I don't think that reduces. And that is, I should have known that was 0.15. I had to look at that. Darn it. Upset with myself. 3 out of 10 is 0.3. That's why I should have known that quick. And then strawberries. 8 out of 20. So this is real Mickey Mouse basic. By the way, I have to teach my seniors how to deal with fractions almost every day. Oh, those seniors are so mad at me. But 4 goes into 8 twice. 4 goes into 25 times. And then that is 0.4. These all add up to 20 over 20, just like these all add up to 1.0. If I made them percentages, they would all add up to 100%. So that's the idea of this. This is one confined experiment with these 20 pieces of fruit. Any probability of grabbing any of those fruits should add up to 100%. Blah, 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 blah. And then rolling dice. 1, 2, 3, 4, 5, 6. This is just one die. These are all 1/6. Then, of course, if you add all these up, this is a 6/6 possibility. All right. And I'm not going to turn those into decimals. You get it. Okay. And then I'll make this real easy on the next one. In a uniform probability model, the probabilities for each outcome are equal. So let's go ahead and label that one right there as a uniform, right? So that's what we have with that one. When they're not equal, they are non-uniform. And then that obviously happened right here. Okay, so just another little term for you there. All right, you'll see these notes take a lot longer than your homework. As a matter of fact, I think some people got done with their homework yesterday after all of this. It's so fast. It's like, all right. Okay, we already did that. Done. I did the arrows, right? Okay, and then there's a big thing about theoretical probability, and there's an opposite to this, experimental probability. Anyone ever hear of a loaded die? Raise your hand if you have. Well, loaded die is weighted. So the heavier side, it's more likely the number above that comes up. The weighted side would pull it, and then this number would come up more than others. So to figure out if a dice is valid, this was actually in the probability movie that I gave you. What's it called again? Prediction by the numbers. But I think I kind of cut it off with your crazy Uncle Larry. Do you ever remember the image of Uncle Larry looking like a shyster, like someone that would take your money from you? But anyway, You roll it, and as long as everything comes up approximately 1/6 of the time after a million rolls, law of large numbers, then the dice is good. But imagine if 5 came up like half the time after a million rolls. That's a loaded dice. All right. The opposite side of 5 is heavier, so that's why 5 is showing up more than others. So I want to get you an idea of what theoretical is compared to experimental. You assume that everything's on the up and up, so we can talk about the theoretical probability of this dice. This is what should happen. All right. Until I run an experiment, I can find out if the dice is good or not. So it's an assumption that all outcomes are equally likely to occur. Meaning, if I rolled a million times, one should come up 1/6 of the time. So I'm going to put in here as like a note to self, the die is legit. It is not weighted. So you're assuming you're dealing with a valid thing when you do theoretical probability. In this case, oh, they love doing this with basic probability. It's either marbles in a bag or socks in a drawer, or, and then you reach in and you grab a sock. What's the probability that the sock is? It's always very common on basic probability questions. So the very first one, probability of purple, this is how it's often written. I'm just being lazy again. We can shorthand it. Probability of pull. Maybe I'll even add a P. There we go. Probability of purple is very simple. First of all, 5, 3, 8, 12, 13, 14, 15. Is that right? 8, 12, 13, 14. Sorry. So I have 14 total marbles. Of the purple ones, there's 4 of them. That's what I'm saying. This is probability 101. But we do have some things coming up that we do have to realize. You do not draw a green marble. So probability of not green, and I'll just stop at GR. Well, there's 5 green. Which ones are not green? All the other ones. So sometimes you could do 1 minus 5 over 14, or 14 14ths over, or minus 5 14ths, changing 1. Or we could just count the not greens. Oh, that doesn't reduce, so I can just stop there. So 9 out of 14. All right, now we're getting into it. Listen and just be ready to answer this question. You draw an orange marble or a green marble. My question is, how many marbles do you have in your hand when you're done? Is it 1 or 2? 1. That's the idea. So they're asking, what's the probability in drawing 1 marble that marble is either orange or green? So now I added English to this. Talking to Mr. Stronowski, yes, this probability is actually reading. You got to read and really figure out in your brain what I'm dealing with. But this is also why the word or means what? Add. That's what happens in probability because of what's happening English wise. Because how many marbles are orange or green? Well, you add those up. That's how many you have total. That's one or the other. Right? That should make sense, I think. But anyway, we'll do it in a probability sense. There's 2 out of 14 that are orange. Sorry, and then green is 5 out of 14. So the probability that when you're done, you have one or the other in your hand should be a half, because that does represent 7 of the 14 marbles, said in a more simple sense there. Now look at the next one. You draw a green marble and then a purple marble without replacements. Bummer. I'll tell you what this means here compared to flipping a coin. This one's intact. So drawing a green marble, I think that was 5 out of 14. What does the word and mean? Okay, now why? It's because now I'm drawing one marble, and then I have this in the first position. Then I'm going back into a bag to draw another marble, and I'm going to see if this uh, occurs. Then, as you draw more and more marbles, it gets less and less likely that you get exactly this and this and this. That's why the probabilities start getting crazy and very small. The other thing is, without replacement, what's this denominator? It's 13 because there's only 13 marbles left. Now, is a green marble a purple marble? No, those are different. So, how many purple marbles are there? 4. A lot of times they ask, what's the probability you get a green and then a green again? Well, if without replacement, this would turn into a 4 as well because there's one less green marble, assuming you got a green marble in the first place. All right, now what I would do is this boom, and then go ahead and multiply across. I think this is 91. By the way, this is said to be a dependent scenario. And I know we're going to have that dependent. The second pick depends upon the first and is affected. The denominator reduced. Fumble. Okay. What is independent? The thing about the coins and the thing about the roulette table. Just because there's been 8 blacks in a row on the roulette table doesn't mean has to be a red next. Red next. They're all independent of each other each spin. Just like flipping a coin, each flip is independent of the previous one. So make sure that happens. I already passed out these sheets. Got these sheets in class for anyone that's absent. We got to get you this deck of cards and dice, but this is only one-sided dice, so this is not that bad. Roll a 6-sided die. Probability of odd. I don't know if I wrote that on those next ones, but fine, just so you know the notation of what it looks like. I think you know that there's 3 odds, right? All right, then here we go. Are rolling a dice and then rolling it again independent or dependent? You tell me. What'd you say? Independent. I didn't hear the "in," I thought at first, because the second die has no effect, is not affected by the first. You have just as likely chance of hitting anything. What does the word "and" mean? It's because you're rolling and then you're rolling again, and you need these 2 things to happen, and that's why the probability is going to be pretty small here. There's a 1/6 chance of rolling a 5, and then an even number, there's a 3/6 or half. But getting these both to happen in successive rolls, there's a 1/12 chance of that happening, which is smaller than 10%. All right, that's the point. That's why "and" is multiply. All right, what's the definition of a prime? A number that's divisible by itself, and what number, everyone? 1. What does that mean about 1? Is it prime or not prime? Write that down right now. And I don't know why. I think the only reason the definition that it is because it's part of the definition of prime. Very strange to me. So it's kind of jerky to ask, what's the probability I pick a prime number? They're really trying to get you and make you understand that 1 is not a prime number in the definition of what a prime number is. So what are the only prime numbers on the dice? Is 2 a prime? Yes or no? 3? Yes, no? 4? 5? 6? No. So there's a 3 out of 6 chance again. I don't feel like writing P of prime off to the left. Then a 3, probability of 3, that doesn't take long. 1/6, ain't no thing, chicken wings. All right, and then flip over on your sheet to the cards. And you might want to do this on your cards here. First of all, those are hearts, diamonds, spades, and clubs. And the ace is on the bottom, but who knows what the ace actually is most times? Or it's actually the lowest or the highest card in a deck. In most games, it's the what card. It's usually used as the highest, except if you're playing poker, it could be both. But when you're dealing with like 4 aces beats 4 kings. So you got to understand that. You don't have to know all that, but hey, What are face cards? Someone tell me that and raise their hand and then tell me why. What are the face cards? Which ones? Okay, so right now I draw a line on your paper and then draw a line and then face cards. How many face cards are there then? That's coming up. There's 12, just so you know that. How many of each suit are there? There's 13. So just make sure you have all these things on. That's why we give you this piece of paper. Because we love using cards as well for probability questions. Really can't think of anything else off the top of my head how you should mark this sheet. The other side is we often have 2 dice questions. And I'm sure they'll be coming up. If not, then we just won't look at that. But back in the day, that's what I used to love asking about. Then here we go. We got our standard deck of cards. So, standard deck of cards, what's the probability an ace? How many aces are there? 4. So the probability of an ace is a 4 out of 52. And then that's 1/13. And then you can make that a decimal or. And then here we go again. What's the probability of a diamond? Well, there's 13 out of 52. So again, this is, what's a diamond look like? Ooh, I'm going to try to draw my diamond. Yeah, a little shaky. Probability of diamond 13 out of 52, which is 1/4, which is 0.25. All right, here we go. Again, how many cards do I have in my hand when I'm done? 1 or 2 for letter C. You have 1. That's the point. So when they ask, what's the probability you get a 5 or a face card? All right. You only have 1 card in your hand. You just want to know what's the probability it's one or the other. That's why you add. So again, we're going to add here. Then this is where this gets a little crazy. But what's the probability of getting a 5? How many 5s are there? 4. And I'm not writing this out, whatever. And then what's the probability? What's a face card? Well, I almost put 13. All right, so this is 16 50-seconds. Oh, I think 4 goes into both of these. 4/13. Now, this is where it gets nuts. This is about coming up, and scary words ready. Get ready to say mutually exclusive. Say it. Oh, gosh, that's good. Oh, this is when this is going to get nuts. Not really. What if I said, what's the probability of getting a king or a face card? What's wrong? What happens here? What's wrong with that? A king is actually a what? Face card. So there's 4 kings, but what would this number have to be? Yeah, you'd have to pull that out because it's it's not mutually exclusive. I already have the 4 kings counted for in the first part, and that's when this gets crazy. That's why we have to add some concepts. Not yet, but I just want you to know we're going to have this question again, and then there's going to be some overlapping, and then you got to actually figure that out. Same thing with this one, but what does the word and mean? What's the word and mean? Multiply. How many cards are you going to have in your hand when you're done? 2. That's the difference between or and as well. I'm getting this card, and then I'm also getting this card after I got this card. So things might be dependent. And when it says without replacement, that means this is a dependent scenario. That means the second is affected by the first. So how many red queens are there? 2 out of 52 times, and then a spade. What is the denominator? And then how many spades are there? 13. Now, here's the problem. What if it said a black queen and then a spade? Oh, now don't even try to answer that because there's 2 possibilities. And then that's where this gets a little bit crazier. When we don't have mutually exclusive events that actually overlap, we got a problem. And that's what's coming up. I just wanted to put that up in your head there that these could get a little bit more complicated. Right now, they're simple. All right, and then you go ahead and multiply 2 over 52, and then, I don't know, I just get a decimal for this. I'll write it up there just to clean up the notes. Yeah, cheating here. We already got the work done. Lost my pen, so we get to see that. It's back. 2 goes into 52, so I could have reduced there. And then, 13 over 51 is 1/4, so I could have done a lot more on that. But 1 over 102. Anyone else get that? Yeah, okay. All right. Good to go.